Have you ever gazed up at the night sky, perhaps on a clear, crisp evening, and found yourself mesmerized by the moon's serene glow? It's a sight that has captivated humanity for millennia, inspiring countless myths, legends, and scientific inquiries. But beyond its beauty, have you ever pondered the enigmatic dance of the moon? It hangs there, a beacon of light against the dark canvas of space, seemingly defying the very laws of nature that govern our everyday lives. Why doesn't it fall to Earth like an apple tumbling from a tree? This question, simple yet profound, has intrigued scientists and philosophers alike for centuries. After all, we know that what goes up must come down, right? This intuitive understanding of gravity, while accurate on a small scale, doesn't quite explain the grander mechanics of our universe. The answer to this celestial puzzle lies in the fascinating realm of physics, specifically in the concepts of gravity, velocity, and orbital motion. These forces work in harmony to create the delicate balance that keeps the moon in its place. These principles, first understood by Sir Isaac Newton centuries ago, explain the delicate balance of forces that keep the moon in its perpetual dance around our planet. Newton's insights into gravity and motion were revolutionary, providing a framework that has stood the test of time. In this exploration, we'll delve into the world of Newton's laws, which describe how objects move and interact with forces. Newton's first law, often called the law of inertia, tells us that an object in motion will stay in motion unless acted upon by an external force. This principle is crucial in understanding the moon's motion. The moon is constantly falling towards Earth due to gravity, but it also has a tangential velocity that keeps it moving forward. This creates a continuous freefall around our planet, resulting in its orbit. By unraveling the interplay between gravity and velocity, we can see how these forces combine to create the stable orbit we observe. Gravity pulls the moon towards Earth, while its forward motion keeps it from crashing down, creating a delicate balance. This captivating phenomenon of orbital motion is a testament to the elegance of the natural laws that govern our universe. Join me as we unlock the secrets of the moon's mesmerizing celestial ballet and gain a deeper appreciation for the intricate dance that keeps our nearest neighbor in the sky. Before we can understand why the moon doesn't plummet to Earth, we must first grasp the fundamental force that governs the cosmos: gravity. Gravity is one of the four fundamental forces of nature, alongside electromagnetism, the strong nuclear force, and the weak nuclear force. It is the force that gives weight to physical objects and causes the tides, the orbits of the planets, and the structure of galaxies. Without gravity, the universe as we know it would not exist. Gravity is an invisible force that attracts any two objects with mass towards each other. This attraction is universal, meaning it affects everything with mass, no matter how big or small. From the tiniest particles to the largest celestial bodies, gravity is at work, pulling them together. It's the reason why we feel tethered to the ground and why objects fall to the earth when dropped. When you jump, gravity pulls you back down. When you drop a ball, gravity causes it to fall to the ground. This force is so constant and pervasive that we often take it for granted, but it is always there, influencing our every move. This force of attraction isn't limited to Earth, it permeates the entire universe. Gravity is what holds galaxies together, what causes stars to form, and what governs the motion of planets and moons. It is a fundamental force that shapes the cosmos on every scale, from the smallest particles to the largest structures in the universe. Every star, planet, and moon exerts a gravitational pull on every other celestial body. This mutual attraction is what keeps planets in orbit around stars, moons in orbit around planets, and stars in orbit around the centers of galaxies. Without gravity, these celestial bodies would drift apart, and the universe would be a very different place. The strength of this pull depends on two key factors: the mass of the objects and the distance between them. The more massive an object, the stronger its gravitational pull. Conversely, the farther apart two objects are, the weaker the gravitational attraction between them. This relationship is described by Newton's law of universal gravitation, which states that the force of gravity between two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The more massive an object, the stronger its gravitational pull. This is why massive celestial bodies like the Sun and Jupiter have such strong gravitational fields. The Sun's gravity is what keeps the planets in our solar system in their orbits, while Jupiter's gravity has a significant influence on the orbits of its many moons and even on the asteroid belt. That's why the Sun, with its immense mass, holds our entire solar system in its gravitational embrace. The sun's gravity is the dominant force in our solar system, shaping the orbits of the planets and keeping them in a stable configuration. Without the sun's gravity, the planets would drift off into space, and our solar system would cease to exist as we know it. Distance also plays a crucial role. The closer two objects are, the stronger the gravitational attraction between them. This is why the force of gravity is much stronger on the surface of the Earth than it is in space. As you move farther away from the Earth, the gravitational pull weakens, which is why astronauts experience weightlessness in orbit. The closer two objects are, the stronger the gravitational attraction between them. This principle is evident in the way the Moon orbits the Earth. The Moon is much closer to the Earth than the Sun, so the Earth's gravity has a stronger influence on the Moon's orbit than the Sun's gravity does. This is why the Moon orbits the Earth and not the Sun, despite the Sun's much greater mass. This principle explains why we feel Earth's gravity more strongly than the Sun's gravity, despite the Sun's vastly greater mass. The Earth is much closer to us, so its gravitational pull is much stronger. This is why we stay firmly planted on the ground, rather than being pulled towards the Sun. Gravity is a fascinating and complex force that governs the motion of objects in the universe, and understanding it is key to understanding the cosmos. Sir Isaac Newton, a brilliant physicist and mathematician, revolutionized our understanding of gravity with his groundbreaking work in the 17th century. Newton's law of universal gravitation elegantly describes the force of attraction between any two objects in the universe. This law states that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. In simpler terms, this means that the more massive the objects and the closer they are, the stronger the gravitational pull between them. Newton's law provided a mathematical framework to explain why objects fall to the ground and why planets orbit the sun. It formed the foundation for our understanding of celestial mechanics and allowed us to predict the movements of planets, moons, and other celestial bodies with remarkable accuracy. Now that we've established that gravity is a universal force, a force that acts between any two masses, we can delve deeper into its effects on celestial bodies. Gravity is what keeps planets in orbit around stars, moons in orbit around planets, and even governs the motion of galaxies. It's a force that is both incredibly powerful and yet, in some ways, quite subtle. And that Earth exerts a strong gravitational pull on the Moon, pulling it towards our planet, with a force that is proportional to the mass of the Earth and the Moon, and inversely proportional to the square of the distance between them. A perplexing question arises: why doesn't the Moon simply succumb to this force and crash into Earth? This question has puzzled many, but the answer lies in understanding the nature of orbital motion. It seems counterintuitive that the Moon, a celestial body under the influence of Earth's gravity, doesn't just fall straight down. Instead, it maintains a stable orbit, a delicate balance between gravitational pull and its own motion. Could remain in a stable orbit without plummeting towards us. This balance is a result of the Moon's velocity, which is just right to keep it in orbit rather than falling into Earth or flying off into space. The answer to this intriguing riddle lies in the Moon's motion. The Moon is not just sitting still in space, it is moving at a high speed tangentially to the force of gravity pulling it towards Earth. The Moon isn't stationary, it's constantly moving through space at a high velocity. This motion is what keeps it in a continuous freefall around Earth, creating what we perceive as an orbit. It's this velocity, combined with the force of gravity, that creates a centripetal force, pulling the Moon towards Earth, while its inertia tries to move it in a straight line. That prevents the Moon from crashing into Earth. Instead, it follows a curved path around our planet, a perfect balance of forces that keeps it in a stable orbit. To fully grasp this concept, we need to understand the principles of motion and gravity. These principles were first described by Sir Isaac Newton, who formulated the laws of motion and universal gravitation. Let's imagine a simpler scenario here on Earth. Picture a ball tied to a string. When you swing the ball around in a circle, you can feel the tension in the string pulling the ball towards your hand. Picture a ball tied to a string. This is a simple analogy to help us understand the forces at play in an orbit. If you hold the string and swing the ball around in a circle, the ball doesn't fly off in a straight line because the string exerts a centripetal force, pulling it towards the center of the circle. You'll notice that the ball doesn't fly off in a straight line. Instead, it follows a curved path, constantly being pulled towards the center by the string. Instead, it follows a curved path, constantly changing direction as it moves. This is similar to how the moon orbits Earth, with gravity acting as the string pulling the moon towards our planet, constantly changing direction as it moves. The moon's high velocity and the gravitational pull from Earth create a continuous curved path, keeping the moon in orbit rather than crashing into Earth.